All right, thank you, Francesco. Also, thanks to Alvaro and Martin and other organizers of this seminar for giving me this opportunity to speak. So yeah, as you can read on the title page, this talk is based on my master's thesis that is supervised by Jon Markut. And it is about Lie groups of Poisson diffeomorphisms. So yeah, a quick overview of the contents. Let us first look at the problem that I've been considering during my thesis, which is on the problem of, well, Poisson diffeomorphism groups. Then we connect it to a linearization problem of Lagrangian submanifolds in Poisson manifolds. And finally, we look at some applications. All right, let's dive immediately into it. So suppose we have a Poisson manifold M with Poisson structure pi. One can look at the group of all diffeomorphisms that preserve the Poisson structure. These form a group, and infinitesimally, there's this counterpart of the Poisson vector fields. These generate sort of the Poisson diffeomorphisms. This is not a full story because this group admits, well, various kinds of interesting subgroups. For example, there are the Hamiltonian ones, which are well defined to be time one flows of time-dependent Hamiltonian vector fields. Well, and what are the Hamiltonian vector fields? Those are exactly coming from the vector fields generated by functions. This is the Hamiltonian function, and then you obtain a vector field from the Poisson structure in this way. Associated to the Poisson structure, you have a symplectic foliation, and therefore, associated to the symplectic foliation, you can look at those Poisson diffeomorphisms that send each symplectic leaf to itself. This is again a subgroup of the Poisson diffeomorphisms, and well, in general, these are not equal. Infinitesimally, these foliated Poisson diffeomorphisms are generated by, well, Poisson vector fields that are precisely tangent to the symplectic foliation. And finally, there's still one group in between, which are the locally Hamiltonian Poisson diffeomorphisms, and those are, well, similarly defined to the normal Hamiltonian ones. These are the time one flows of locally Hamiltonian vector fields. Well, and what are locally Hamiltonian vector fields? Locally Hamiltonian vector fields is in this case, well, defined by, is locally given by a Hamiltonian function, or you can alternatively describe it by it being the image of a closed one form. So, well, this is already, there are quite some things going on over here. So let's have a look at some examples where that might be more familiar. If you have a symplectic manifold, then, well, we have certainly the Hamiltonian ones. We have the connected component of the diffeomorphism group, the symplectomorphism group, that is. And if you look at these other subgroups, the locally Hamiltonian ones actually coincide with this. And here, the foliated ones are in between. And there's not much going on this side. By the way, this should be the connected component, the identity component of the foliated diffeomorphisms. And the difference between the Hamiltonians and the symplectomorphisms is described by, is governed by the first cohomology. On the other extreme, you can look at the Poisson manifold with the zero Poisson structure. In this case, well, all the subgroups that we mentioned are trivial, except for the Poisson diffeomorphism group. And that one is immediately coincides with the full diffeomorphism group. So this already shows that, well, the subgroups can, well, can be quite different. So now I can introduce the problem. Can we make sense of the Poisson diffeomorphism group as a Lie group? And by Lie group, we mean an infinite dimensional Lie group. And also, make sense of here means that its Lie algebra should coincide with the Poisson vector fields. And well, you can also ask the same question about its subgroups. Before we dive into this problem, we first look at how well a manifold structure or a Lie group structure is obtained on the full diffeomorphism group. So how does this go? The crucial insight for that is the following. If you have any map from M to M, it introduces a graph in the product, which you can view as a submanifold. So you can view it in the picture as, well, it goes something like this, like the red line. Now, if you look in the tubular neighborhood of the diagonal is exactly the graph of the identity. You can identify those submanifolds nearby that look like a graph with sections of the normal bundle. So you get a sort of identification with sections, which is a linear space, a vector space, and diffeomorphisms that are close by. Now, finally, the observation that the normal bundle is exactly the tangent bundle, you have around the identity modeled your diffeomorphism group on the space of vector fields, which is exactly what we want. And as a conclusion, you can prove that the diffeomorphism group is an infinite dimensional Lie group with Lie algebra given by the space of vector fields with Lie brackets, with the usual Lie brackets. So more generally, you can look at bisections of a groupoid. So bisections of a groupoid are a sort of generalized diffeomorphisms. And indeed, if you want to construct charts for this one, it goes in a very similar way. So what is exactly a bisection? If you have a groupoid G with a source and target map denoted by S and T, then a bisection is just a section of the source map, such that if you compose it with the target map, you get a diffeomorphism. These form a group, and similar to the diffeomorphism group, you can look at bisections that are close to the identity, which are now the identity bisection is now just a space of units in G. And in the same way, when you look in the tubular neighborhood, you can model it on a space of closed sections, of sections close to zero. Now, the observation that the normal bundle of the units is just isomorphic to the Lie algebroid, associated to the Lie algebroid, you can prove the following, which is that the bisections of G is a Lie group with Lie algebra given by the sections of the Lie algebroid equipped with the Lie brackets. All right, so far so good. Let's look at the.
Sorry, Wilmer, there is a question in the chat related to what you were saying.
Yeah.
Pedro was asking, what is the topology on charts?
The topology on the charts. So yeah, you can basically you topologize this space of sections. Yeah, okay, I should mention two things. If M is compact, so then you can model the space of sections with topologize it via the C infinity topology. And then you use just all these charts together to induce a topology on the group of bisections. So over here, we constructed a chart around the identity, but you can more generally construct a chart around any bisection. Now, if M is not compact, then you need to look at compactly supported sections. And those have a bit finer topology where you declare, well, they declare sections that agree in a compact set to be that agree out of a compact set. Those bisections you declare to be those equivalence classes you declare to be open. I hope that answers the question a little bit. In that case,
say thanks.
Right, good. And,
sorry, Wilmer, but sorry, do you get like this strong C infinity topology if you do what you said on the non-compact manifold M?
No, it's even it's even finer.
Okay, it's even finer than that. I see.
So if you look at the identity component, it consists of all compactly supported bisections, basically. So the identity component consists of those bisections that are just the identity outside a compact set, and that is much finer than
okay. It's even finer than the strong infinity. Thanks.
So what about the symplectomorphism group? In that case, we can characterize the graphs nearby that come from symplectomorphisms in a very geometric way, which is the following, namely that the diffeomorphism is exactly a symplectomorphism when the graph is a Lagrangian submanifold when we endow the product with this kind of product, symplectic structure. And how do we describe the Lagrangians nearby the diagonal? For this, we appeal to the Lagrangian neighbourhood theorem to obtain a local symplectomorphism between the cotangent bundle equipped with the canonical symplectic form and a product manifold. And this is local means that it's defined in a tubular neighborhood of M near the diagonal. In this tubular neighborhood, we can identify symplectomorphisms, which we identified with the graphs, Lagrangian graphs, with closed sections of the cotangent bundle. Because you may remember that a section of the cotangent bundle is closed if it's Lagrangian if and only if it is closed. So this way we build a chart on the group of symplectomorphisms around the identity, and we can give the symplectomorphism group the structure of a Lie group. Now let's finally go to Poisson manifolds. The story starts in a similar way. So if you start with the graphs of Poisson diffeomorphisms, we can again characterize in a very geometric way, namely that the graph of a Poisson diffeomorphism, is coisotropic if and only if the underlying diffeomorphism is Poisson. So this is a nice geometric characterization. So if you want to describe the Poisson diffeomorphisms that are close to the identity, then we're really looking at coisotropic deformations of the diagonal inside this product. However, these coisotropic deformations are rarely easily described. So, well, in only a few cases we can say something about that. So we need to come up with a different strategy, which is the following. Let's start not by looking at the product, but that a bit more generally to a Poisson groupoid. In this case, we can look at coisotropic bisections of this Poisson groupoid. So remember that bisections, you could look at bisections, and if the image of a bisection is a coisotropic manifold, submanifold of the Poisson groupoid, then we call it a coisotropic bisection. These actually form a subgroup of the total group of bisections. Now, there's a nice interplay between those coisotropic bisections and Poisson diffeomorphisms, namely that any coisotropic bisection induces a Poisson diffeomorphism on the base. In a similar way that we looked at the diagonal, is that the local nature of the bisections, the coisotropic bisections of a groupoid is.
Neem me niet kwalijk.
Yeah.
What's the relationship between the big pi and little pi?
So, if you have a Poisson groupoid, there is a unique Poisson structure on the base manifold for which the source target is a Poisson map. And this small pi is this induced induced Poisson structure on the base.
Thank you.
All right. So the local nature of this group is again about coisotropic deformations of the space of units inside of our Poisson groupoid. Well, again, these are hard to describe, but we may have some more opportunities because we're looking at more general Poisson groupoids than just the product groupoids. So we can now formulate a strategy. So if we start with this Poisson manifold M, we want to find a Poisson groupoid over this Poisson manifold, so that the group of bisections is an interesting group. And what do we mean by an interesting group? Namely, that this induced homomorphism either surjects on one of those subgroups that we introduced before, or maybe is in one-to-one correspondence, or gives a bijection between one of those subgroups. Something interesting, something that something that from which you can obtain information about the Poisson diffeomorphisms. Well, and secondly, we want to be able to describe this group of coisotropic bisections as a Lie group. So that's the general strategy. So how do we address the second part? So as I told you before, the local nature of this group is really about the coisotropic deformations. So let us study a little bit more a certain case when these coisotropic deformations are particularly nice. And this and that way we come to linearization. So let us first remind you all that any Lie algebroid over some manifold L induces a linear Poisson structure on the total space of its dual. All right, so we need this kind of correspondence. It's even the other way around. If you have a linear Poisson structure on the total space of its dual, then it induces a Lie algebroid structure over here. All right, so what happens when we have a coisotropic submanifold of a Poisson manifold pi? Then the conormal bundle, which is the dual of the normal bundle, is a subalgebroid of the cotangent algebroid coming from the Poisson structure. Now this way we obtain a linear Poisson structure on the normal bundle of L. And this linear Poisson structure is called the linearization of pi around L. The upshot is why we're looking at linear Poisson structures is that if pi is linear, then the coisotropic deformations of L form a linear space. And if you can describe the coisotropic deformations by a linear space, then, well, we can build a chart on our group of coisotropic bisections. So that's where we're heading. But not every well, there's some abstraction. This linearization does not always happen and cannot always occur around the coisotropic submanifolds. First of all, if pi is linear, then this L must be a Lagrangian. And what does Lagrangian mean in this case? Its symplectic orthogonal is as large as it can get. I don't know, do you see those red lines? I don't know where they come from. On the slide.
Yeah, they are there. I don't know why either.
I think somebody made them by accident, and you can always, I think, delete them if you made them.
I think probably they will disappear in the next slide because it could be one of those like the blackboard.
If somebody else did it, they don't. The same person who did it should erase them.
Yeah.
Yeah. Do you have kids, Wilmer?
Maybe it's the cat. No.
So please, if somebody did it, erase them. But otherwise, well, we can still read the rest. So.
You can also stop sharing and start sharing again.
But I think if he goes to options, goes to annotate, and then put clear, the speaker can erase everything.
Annotate. Oh, this works. And then
and then clear.
Yeah. Oh, thanks.
But what happened?
Some red line appeared.
Yeah.
The lines you put there, Marius, and he took them out.
I actually, it's right. I may have done it because I had to put it on hold on my phone. I had to answer something, and then I had to press a pen. Yeah, sorry guys. I think it's my fault.
Oh, all right. Well, now it's cleared up. That's good. All right. Well, we were on the verge of introducing the linearization problem. So recall that around any coisotropic submanifold, we had an induced linear Poisson structure on the normal bundle. And now we can ask, if we start with a Lagrangian submanifold, when is this linearization locally isomorphic to the Poisson structure we began with? So this is some sort of extension of the linearization problem of the zeros of a Poisson structure, where Kahn's theorem provides a partial answer. But the case of Lagrangian submanifolds is a bit different because the Poisson structure itself does not need to vanish on L. And some other people also have been working on this problem. And for that, I want to mention especially Aldo Witte recently had a result in this direction. And also by discussions with him, this problem I became aware of this problem. So now, do we have any chance of linearizing the Poisson structure of a Poisson groupoid around a space of units? Well, some chance. The space of units in a Poisson groupoid is always a Lagrangian submanifold in the sense above. So that's good news. So yeah, this sort of canonical example for linear Poisson structures is the one that is the linear Poisson structure that is dual to the tangent bundle. And I want to go over this in a slightly more detail because this will be important next, where we generalize it to other algebraics. So this TL, the tangent bundle of L, well, it's a Lie algebraic. It's basically the basic Lie algebraic. So this means that on T star L, we have a linear Poisson structure, but this can be described in a different way. Recall that on the cotangent bundle, we had this canonical 1 form, which was defined really well in the only way possible. If you have a tangent vector, you apply the projection map and then evaluate it at the point where you look where you investigate the 1 form. In the symplectic form that you obtain this way by taking the differential induces the linear Poisson structure on T star of L. Well, that's interesting because this means that the linear Poisson structure obtained from this one is always symplectic. Furthermore, we can describe the coisotropic deformations this way, namely the image of a section is Lagrangian if and only if it's closed. The Lagrangian neighbourhood theorem states that symplectic structures are always linearizable around Lagrangian submanifolds. So now let's look more generally at the Lie algebraic. So let's start with the Lie algebraic A over L and let P be the projection from its dual to L. The Lie algebraic, if you pull back the Lie algebraic A to its dual space, then this one carries a canonical 1 form, defined in a very similar way. At a point in A star, namely alpha, we can look what and V in the fiber of these pullback algebraics. We can evaluate them if we move this V that's in the fiber over here to A itself. So this is again a perfectly well-defined 1 form. Now the 2 form that we obtain by taking the algebraic differential this way is a symplectic, which means that it's closed and non-degenerate as a algebraic form, and it induces the linear Poisson structure in the following sense. In the sense of this diagram commutes. So the anchor map coming from the linear Poisson structure can also be obtained by going by going to the dual and then, well, moving along this diagram via the symplectic structure. And now we can describe the Lagrangian deformations of L, namely the image of a section of the image of a section of A star is Lagrangian if and only if it's closed as a algebraic form. And now you need one more thing, namely that the coisotropic deformations of L of the zero section in A star, in this case, are always the Lagrangian. Always Lagrangian. So this happens in linear Poisson structures. This phenomenon was already observed by De Leon, Marrero, and Martinez in a paper they published in 2004. But it's not. I have not seen it on other places, so I don't know how well known this is. We can also extend the Lagrangian neighbourhood theorem to the setting of Lie algebroids this way. But for that, we need the right notion of a Lagrangian in this case. So if we start with a symplectic Lie algebroid, which just means a Lie algebroid A with a algebroid 2 form that is closed and non-degenerate, then a Lagrangian transversal is just a submanifold of M that is transverse to the algebroid, and the pullback of the algebroid is a Lagrangian subbundle of our algebroid itself. Any Lagrangian transversal induces a Lagrangian on the base, Lagrangian for the induced Poisson structure. Now we can formulate the following theorem. If you start with a symplectic Lie algebroid and a Lagrangian transversal, then around this Lagrangian transversal we can linearize the Poisson structure. We can linearize it even on the algebroid level, namely that there's a local symplectomorphism, which is in this case an algebroid isomorphism. And local means that it's around a neighborhood. Oh, this should be L. Oh no, this should be M. Yeah, this should be M. In the neighborhood of L, such that it's well, it pulls back the canonical one form to the symplectic form we started with, and it restricts to the identity on L. So a few comments about the proof of this. It heavily relies on the splitting theorem for Lie algebroids, which is basically a linearization theorem for the, it says that if you have a Lagrangian transversal, then you can linearize the algebroid around this your submanifold. And this was done by Burstein, Lima, and Meyrecken in 2017. And it during the proof you need some sort of Moser-Weinstein stability result on symplectic Lie algebroids. And this was also announced by Raya Shamar in a conference in Toronto in June this year. But then mainly the arguments from the symplectic case carry over if you use, well, if you have the right ingredients. And this theorem sort of summarizes a phenomenon that has been occurring in the literature so now and then, and it puts it under one umbrella. Well, first of all, it reproduces when the algebroid is just Tm, it reproduces the usual Lagrangian neighborhood theorem. If we have a symplectic foliation, so the algebroid's foliation, then L, a Lagrangian transversal, means that it's transverse to the foliation, and we have a sort of foliated version of the Lagrangian neighborhood theorem. And this also, well, appeared in the literature now and then. If the algebroid is the B tangent bundle that we saw from last talk, then transversal means that L is transverse to Z. And in this case, you have a Lagrangian neighborhood theorem adjusted to the B setting. And you can also do this for other Poisson structures like BK, the BK tangent bundle, elliptic tangent bundle, etc. And it all puts these kind of neighborhood theorems under one umbrella. All right. Any questions at this point? Let me then continue. We want to apply this, and ultimately we were looking at Poisson diffeomorphisms, and this linearization theorems were just a tool. So let's go back to Poisson diffeomorphisms again. And the first application has also been the main inspiration for the strategy we follow. If you have an integrable Poisson manifold, then you can look at the symplectic groupoid. In the symplectic groupoid, the coisotropic bisections are exactly the Lagrangian bisections. These form a subgroup of the total space of bisections. And using the regular Lagrangian neighbourhood theorem, you can build a chart on the group of Lagrangian bisections. Yeah, and it's modeled. This chart is modeled on the closed sections of T star M. This way, the group of Lagrangian bisections is a Lie group whose Lie algebra is given by the closed one forms equipped with the brackets induced by the Poisson structure. So that's interesting. And there are also some intimate connections between Poisson diffeomorphisms. Namely, you can also introduce the notion of exact bisections, and these sit inside the normal bisections. There's the induced homomorphism that I introduced before, lands in the locally Hamiltonian group. This morphism is always locally surjective. And furthermore, the exact bisections these sort of cover the Hamiltonian group. On the infinitesimal level, it's given by the Lie algebra morphism by Sharp. So that's the infinitesimal picture. So these Lagrangian bisections have been studied by Ping-Su already in, some 20 years ago in Ribici. And yeah. So let's look at the next application of log-symplectic structures. So well, we saw already quite some log-symplectic structures from in the previous talk, but let me still recall briefly what those are. So Poisson structure pi on a manifold is log-symplectic if it degenerates almost everywhere except if it's non-degenerate almost everywhere except along a hypersurface, or you can express it in a sense that the determinant at the highest wedge product of this Poisson structure is transverse to the zero section. Yeah, so this pi is symplectic away from a hypersurface, and on this hypersurface it induces a codimension 1 Poisson structure. Now, alternatively, one can describe this log-symplectic structure as a symplectic form on a certain algebroid called the log-tangent bundle. And this log-tangent bundle is the algebroid whose space of sections is are exactly the vector fields tangent to Z. So this log-tangent bundle incorporates the infinitesimal symmetries of everything that happens on M, but tangent to Z. Not parallel, but tangent. Yeah, so in any log-symplectic structure comes from a symplectic form on the B tangent bundle. So, well, let's try to build a manifold structure. So we look at a product, and we have the diagonal over here, and we immediately run into some trouble because this product Poisson structure on M times M is not linearizable, is never linearizable, in fact, around the diagonal. This is because, yeah, the product has some sort of normal crossing singular hypersurface, and this diagonal goes exactly through this normal crossing. If you look at the linearization of the Poisson structure around the diagonal, then it has no normal crossing. So this means that well, this Poisson structure cannot be linearized. So we need to do something else, and that's a blow-up construction. So we basically perform a blow-up construction at the points where it goes wrong. So in Z times Z, where it's not linearizable, we blow this up, and we obtain a new groupoid, the pair Z of M, which is called the log pair groupoid. Well, almost. We need to remove some parts, but I will not go into much detail about that. So the red striped parts are removed. So this construction was considered by Gualtieri-Lee in the paper on symplectic groupoids of log-symplectic structures, log-symplectic manifolds. So when there they deduced that this log pair groupoid is a Poisson groupoid, and the induced Poisson structure is in fact log-symplectic. The space of units is in this case transfers to the degenerate locus of pi. And the degenerate locus of pi is exactly the green circle you see over here. Now, we had, in this case, because this transfers to the degenerate locus, we can apply our version of a Lagrangian neighbourhood theorem, but now in the B setting, to obtain a manifold structure on the group of coisotropic bisections. So why are those bisections interesting? We can, well, those bisections exactly compute the diffeomorphisms of M that preserve the hypersurface. So you can maybe see this a little bit. If you have a diffeomorphism that preserves the hypersurface, then its graph must go through this normal crossing. Well, this means that it's lifts to the blow up, and we get a bisection on the blow up. Yeah, therefore you can introduce you can identify the bisections of this log paragroupoid with diffeomorphisms preserving Z. And using the Lagrangian neighbourhood theorem in the right tubular neighborhoods, we can pick out the coisotropic bisections. And these coisotropic bisections exactly correspond with the Poisson diffeomorphisms. So our theorem is now that the group of Poisson diffeomorphisms is a Lie group whose Lie algebra is given by the B closed one forms, but via the symplectic structure, this is exactly these are exactly the Poisson vector fields. So this is so somehow what we wanted. And this is not a full story, because there are some of those subgroups that we've been looking at. So what about those? Well, infinitesimally, you can look at the closed, infinitesimally the log-symplectic structure induces an isomorphism between Poisson vector fields on one side and B closed one forms on the other side. If you look what this isomorphism does on the closed one forms, which sit inside the B closed one forms, then we obtain exactly the foliated Poisson vector fields. And note that this also should be the locally Hamiltonian ones. Because of this isomorphism and the fact that the Lagrangian bisections of a symplectic groupoid is a Lie group integrating this Lie algebra, we should look at the symplectic groupoid to somehow say something about the foliated diffeomorphisms. So under some additional assumptions on the log symplectic structure, you could obtain a symplectic groupoid by performing another blow-up construction in the log pair groupoid. This way, we get a isomorphism between the foliated Poisson diffeomorphisms of the log symplectic manifold and the Lagrangian bisections. Well, almost an isomorphism for all practical purposes. So there could be some connectedness issues. But what is true is that the foliated diffeomorphisms are always a union of components of the group of bisections. So for all practical purposes, these are the same. Now to complete the full story, for log symplectic manifolds, on the bottom row we have our four groups of Poisson diffeomorphisms that we were interested in. And above we have always a group of Lagrangian bisections or coisotropic bisections. So we started with by looking at the group of full Poisson diffeomorphisms, And these were obtained by the coisotropic bisections of the log pair groupoid. Now, if you go back to the symplectic pair groupoid, then we obtain the foliated diffeomorphisms. If you look at the identity component of this group of Lagrangian bisections, then these correspond exactly to the locally Hamiltonian diffeomorphisms. And finally, if we then descend to the exact bisections, we get the Hamiltonian diffeomorphisms. So that's the story for log-symplectic manifolds. Now let's see how I'm on time. I'm a bit over time. I'm sorry, but I have one more slide.
Don't worry.
I want to mention that I've also been looking at scattering manifolds, which are sort of Poisson manifolds that with a bit of with a higher order degeneracy around a hypersurface. And in this case, all of the groups are different. So yeah. You can also prove that Poisson structures coming from co-symplectic structures those form a Lie group, and Poisson manifolds of strong proper type. Those Poisson diffeomorphisms also form a Lie group, and this is actually an application of the recent linearization theorem by Algebraic that I mentioned before. Yeah, and I guess that this is what I wanted to talk about, and this is now my current current status of my master project. So thank you for listening and your interest.